Hello seniors, today we're going to see electronic assignment 27, which is about area and definite integrals. We're going to see how we can find the actual value of an integral and what that means. We're going to see the first real application of integrals, which is, as the name says here, finding the area under a curve, right? If you remember, derivatives was very useful in order to optimize values, right? Finding maximum and minimum points. The integral is useful to find areas and later on volumes of different curves or different shapes, okay? That's the main application of integrals. So that's what we're going to see today. So objectives for today's class: number one, calculate definite integrals, both analytically and using technology. I'm going to show you how to use your calculators to find definite integrals. And number two, find areas and their curves. Between the curve and the x-axis, applying integrals. Okay, so let's start by doing this small investigation here. It says, consider the area bounded by the function f of x equals x squared plus 1. So this is this red curve over here, right? And the straight line x equals 0, which is, actually this should say y equals 0. X equals 0, so from here to x equals 2, which is here, okay? So basically we're looking for this green region over here. It says, A, write down the width of each of the four rectangles shown in the graph. So we're not going to be doing this because we're going to waste too much time, but imagine that if you want to calculate the area of this green region over here, we can, for example, trace small rectangles that try to replicate the green area, right? You see that it's not perfect enough because we have small gaps here, which are going to make our value of the area a little bit imprecise. But we're going to see this in order for you to understand what the integrals is about, right? Then it says, calculate the height of each of the four rectangles, find the sum of the areas of the four rectangles, and find a lower bound of the area of the shaded region, okay? So you can, if you want, do this on your own in order to understand what's happening, right? Then if we do the same thing, but now we trace rectangles that go above the curves, we're going to have these rectangles over here. So once again, you can calculate the areas of these rectangles and then add them all up in order to have an upper bound of the area, right? So it says, write down the width of the four rectangles shown in this graph, calculate the height of each of the four rectangles, find the sum of the areas of the four rectangles to find an upper bound of the area of the region, okay? So basically we're doing this just to say that the area of the green region, which is this one over here, can be estimated by doing the average between the areas of this first situation where we drew rectangles smaller than the curve, and the average between the area found by these rectangles which go above the curve, right? If we find the average, we will be estimating kind of the area shaded in the green part, okay? So it says, then use your GDC to evaluate the definite integral, and I'm going to show you this, how you do this. But, okay, here it says, the GDC uses an approximation method to determine the values of definite integrals, so the values from the GDC are not always exact. Okay, so here I put a summary of the values of the areas using this investigation. And you see something. If I draw four rectangles, which is exactly this situation here, four rectangles below and four rectangles above, you would see that the average, I find the lower sum and the upper sum. So if I find the average between these two values, then I will be getting an estimated value for the area, right? And you see that as I increase the number of rectangles, the more rectangles I use, you see that the lower sum and the upper sum tend to the same value, right? They tend to this value over here, 4.66667, okay? So if we draw infinite triangles, we will be getting as lower sum and as upper sum, we're gonna be getting this value over here, 4.66667, right? And that will be the exact value of the shaded region here in green, okay? So the area below the curve would have this value over here if we were able to draw infinite rectangles, but it'll be a waste of time. We will be using too much time doing so, right? We cannot draw infinite triangles because it will take too much time. So in order to find the exact area, we can use integrals in order to find the exact area, right? So if we find this definite integral, we're going to be getting the value of the exact area. But how do we do that? Well, in order to do that, we need to apply the concept of definite integral, okay? And that's what I'm going to show you right now in the calculator. So we're going to replicate this, what we have here, in order to find the definite integral, okay? So give me a second. Let me write some steps here that you will need to follow in order to find the definite integral. So using the calculator, how do we do this? You would have to do the following. You're going to press math, the button that says math, which is F4. Then you're going to click on the small arrow, which is like this, which is F6, I think. The button F6. Then you're going to click on the button that says integral of dx to find a definite integral, that's F1. And once you're done with that, you're going to plug in the function, plug-in function, and the boundary values, right? Boundary values. Okay, so let's try doing that with our calculator. Let me show you. Okay, so if you take a look at the calculator, we're going to follow these steps. First, we're going to click on math, which is F4. Then you're going to click on the arrow, this one over here, which is F6. And here you see the integral sign, right? So you click on F1, you have the integral sign. And here, you're going to copy the function. In this case, the function is x squared plus 1, right? This value over here, x squared plus 1. So you write x squared plus 1. And then you need to define the limit of integration. In this case, we're finding the integral from 0 to the value 2, okay? Here it says f of x equals x squared plus 1 from x equals 0 to x equals 2. So that is our boundary. So from 0, which is the value you put down, to 2, which is the value you put up. You click on execute. Sorry, I forgot to put parentheses here. You should always put parentheses in order to have, for the calculator to be able to read this. There you go. So you click on execute. No, actually, the mistake is that I wrote x incorrectly. We should use this x over here. There you go. So you click on execute, and there you have the value 14/3, which, as you can see, is 4.666667, right? Which is the exact value of the area of this shaded region. So using the calculator, we're going to get to the conclusion that the integral from 0 to 2, of x squared plus 1 with respect to x is equal to 14/3, which is equal to 4.67. So this is how we use the calculator in order to find a definite integral. You can only use the calculator to find definite integrals. You cannot use it to find an indefinite integral because that's an expression, not a numeric value. Okay, and I'm gonna go ahead a little bit, and I'm gonna show you already how to find a definite integral by hand. If you want to find a definite integral by hand, let me write this down. It's from 0 to 2 of x squared plus 1 with respect to x. And to find this, we're going to first integrate this expression just as we know, right? If we find this integral, this would be x cubed over 3 plus x plus c. Don't forget plus c. But now you would see that the plus c will get eliminated because we need to evaluate this integral from 0 to 2, according to our expression, right? So we evaluate this, and how do we do to evaluate? We just need to replace. First, we replace the x values with 2, so this one over here and this one over here with 2, and then we subtract it by the same function but evaluate it now for 0, okay? So that's what we're gonna do. So this would be 2 cubed over 3 plus 2 plus c minus the same expression but now evaluated with 0, right? The lower boundary, so this would be 0 cubed over 3 plus 0 plus c. So you see that here the constant value c actually is getting eliminated. C minus c, so we eliminate the constant value. That's why we do not consider the constant value anymore when we talk about definite integrals. Okay, so this is equal to, and if we solve this 2 cubed, that's 8 divided by 3, that's 8 over 3 plus 2 minus, and this is 0 plus 0, so we get minus 0, right? Minus 0. And if you solve this, you would see that 8 thirds plus 2 is actually 14 over 3. And that's the same result we got here, okay? So that's how you evaluate a definite integral by hand, okay? You're gonna be practicing with exercises about this later on, but that's how you find a definite integral, briefly, okay? So let's continue with this. Then it says, we cannot use a geometric formula to find the area of the region in question 1. You see that this is a curve, right? And we do not know any geometrical formula to find the green area here, right? Because it's an irregular shape. So it says, we can only use geometric formula to approximate the area, right? Now we will consider some regions whose area can be found geometrically. So let's see how that works. It says, find the area of the shaded region under the line f of x equals 2x plus 2 between x equals -1 and x equals 2. So now we want to find this blue shaded region here. And as you can see, this is a known geometrical figure, right? It's a triangle. So we're going to try using both integrals and using the geometric formula we know for calculating the area of a triangle, and compare both just to see if this actually works, okay? So it says, then write down a definite integral you think may represent the area, and then evaluate this integral on GDC and compare answers. Okay, so if we zoom in to this figure for a second, we know how to find the area of this triangle here. The area of a triangle is always base times height divided by 2, right? So area equals base times height divided by 2. In this case, the base would be this segment over here, which is from -1 to 2. So we move on 1, 2, 3 spaces. So the base is 3. The height would be from 0 to 6. So we move on 6 places. So the height is 6, and then divided by 2. So the area of this figure is 3 times 3, which is 9. That's how we geometrically calculate the area. But now let's try finding this same area by doing with the concept of integrals. To find the area, we would find the integral from -1 to 2, right? From x equals -1 to x equals 2, from -1 to 2 of this expression over here, right? Of 2x plus 2 with respect to x, okay? So if let's use a calculator for this. So I'm going to project calculator. So if you take a look at the calculator right now, we're going to do the same thing. The integral of, we're going to write the expression here, 2x plus 2, and we're going to evaluate this from -1 to 2. And you'll see that as an answer, we get 9. Which is exactly the same result we got using the geometrical formula. So once again, you can clearly see here that the area of a given curve can be found using using the concept of integral. Sorry, that's what I meant. Okay, so that's one of the most important applications of integrals. Now, let's move on. It says for number 3, we refer to the area between a function f and the x-axis as the area under the curve. If f of x is a non-negative function and x is defined between a and b, then write down the definite integral that gives you the area under the curve from x equals a to x equals b, which is exactly what we did here. Then verify your answer from question 3 works for the following by finding the area using a geometric formula and then writing down a definite integral and evaluating it on a GDC. Okay, so let's do the same thing we did here, but now with these two figures, okay? So let's see if this works. So we have this function, this red line, which is defined as negative 1/2 x plus 3. And we want to find the shaded region here, which is from x equals 1 to x equals 4. Okay, so how do we do this? If we want to find the area using the geometrical figure formula, we need to identify that this is a trapezoid, right? If you remember from a trapezoid, let me write this first. This is a trapezoid. If you remember the formula for the trapezoid, the formula for the area of a trapezoid is base 1 plus base 2 divided by 2 times height. If you remember the formula, you can apply this, right? Where base 1 is this over here, base 2 is this over here, and the height is this one over here, right? So if we apply the formula, we're going to say that the area of this trapezoid is base 1 is 3, right? 3 plus base 2, which is from 0 to 1, so plus 1. Actually, I see that this is 2.5, right? And this one over here is 1, okay? So let's change that. This is actually 2.5 here, 2.5 plus 1 divided by 2. And the height is from 1 to 4, so that's 3. So times 3. So if we calculate this, you should get an answer of 5.25. This is the area using the geometrical formula. But now let's find the area using the integral rule, right? We can say that the area of this trapezoid is the integral from, we need to define our x boundary. It's from 1 to 4. So from 1 to 4 of the function, which is negative 1/2 x plus 3, negative 1/2 x plus 3 with respect to x. So if we use our GDC, let's use the GDC. Let me show you. So if we plug in the information, the integral, I'm going to write the expression, which is negative 1/2 x plus 3. This is our function, and we want to integrate this from 1 to 4. You click on execute, and then you get the value 21/4, which is 5.25. Okay, so this is equal to 21/4, which is the same as saying 5.25. So you see how this actually works, right? We're finding the area under the curve by using definite integrals. You see that the difference between definite integrals and indefinite integrals is that we now have boundaries for integration. We define an initial value of x and a final value of x, and that's why we call this a definite integral. Okay, so let's see a second case. We want to find the area below this curve, right? And this is a semicircle. So let's identify the figure first. This is a semicircle. So if you remember, if we want to find the area of this figure, if I want to find the area of this figure geometrically, the area of a circle is pi r squared, pi times r squared. But since this is a semicircle, half of the circle, we divide this by 2. Okay, so what is the radius of this circle? The radius of this circle is equal to 4, right? So if we want to find this area, this would be pi times 4 squared divided by 2. This is 16/2, which is 8 pi. So 8 pi is the area of this figure using the geometrical formula. But if we want to find the area using integrals, here we have the function that describes this function, okay, or this curve. So if we want to find the area using integrals, we're going to say that this is the integral from Negative 4 is our initial value, and 4 is our final value. So from negative 4 to 4 of the function, which is the square root of 16 minus x squared, we integrate this with respect to x. Okay, so we go back to the calculator, and now we're going to say that we're going to find the integral of the square root, so square root of 16 minus x squared, right? Minus x squared. And we want to integrate this from negative 4 to 4 according to our problem. So you click on execute and you see that we will get 25.13, which I think we could change. No, we cannot change. So this is equal to 25.1, let's say, right? And if you put 8 pi just to check if it's the same value, you would see that 8 pi is actually equal to the same thing, right? 25.132, okay? So this area we found geometrically, using the geometrical formula, is 25.1, and we get exactly the same result, okay? So I think this is clear, right? We can find the areas under curves by using the concept of definite integral. Okay, so let's move on. Then it says, this is a theoretical part of this. It says, in the investigation, you approximated the area under a curve f of x equals x squared plus 1 from x equals 0 to x equals 2 by summing the areas of 4 rectangles. Using sigma notation, we can express this as the sum of the areas of the rectangles from 1 rectangle to 4 rectangles, adding the areas of 4 rectangles, where f times xi represents the height of each rectangle and delta xi represents the width of each rectangle. To get better approximations of the area, we can use more rectangles. Using an infinite number of rectangles, which is the limit when n approaches infinity, of the sum of the areas of all triangles leads to the exact area. This is just as I told you, theoretical explanation of what the integral represents. So if a function f is defined from a to b, and we find the limit of the sum of all of the rectangles we can have, and that value exists, we say that f is integrable from a to b, and we call this limit the definite integral and denote it as the limit of the sum of the areas of infinite triangles. And this is the same as saying the integral of the function from a to b. The number a is called the lower limit of integration, and the number b is called the upper limit of integration. So here's a summary of what we just read. It says, when f is a non-negative function, we're going to explain why it says non-negative later on. When f is a non-negative function between a and b, then the integral of the function from a to b gives the area under the curve from x equals a to x equals b. So that's how integrals are useful, right? If we find the integral of this function from a to b, we're finding this blue region over here. Okay, so let's see the following example. It says, write down a definite integral that gives you the area of the shaded region and evaluate it using calculator. Whenever possible, find the area using geometric formula to verify your answer. Okay, so we're going to be doing the same thing we just did in the investigation above. So for part A, we want to find the area of the green region here, right? We see that it is a triangle. If we find it geometrically, we're going to say that the area is 1/2 base. The base in this case is from -2 to 2, so we move 1, 2, 3, 4 spaces. So our base is 4. And the height is 2, right? We move two spaces up. So if we simplify terms, we're going to get that the area of this figure is actually 4, right? Now let's see if we get the same result by integrating this expression. You see that we have an absolute value here. And you'll see that our calculator can also find that integral. So if we want to find the area using the concept of definite integral, we're going to say that the area is equal to the integral from -2 is our lower limit, 2 is our upper limit. So from -2 to 2 of the function, which is 2 minus the absolute value of x, with respect to x. You see that the shape of the function in this case is straight, like this and like this, right? And that is caused because of the absolute value function. So if we plug in this into a calculator, once again, we're going to click on integral, and we want to integrate the function 2 minus, to write the absolute value, you have an option, I think, I don't know where it is. There's an option that says apps. I cannot find it, so we're going to go to, you need to click on, if we go back, sorry, it's the, let me write this back again, math integral, and the function is 2 minus, so we're going to go to math apps. There you have f of f3 gives us the absolute value, and then you click on x. That's how you write the absolute value. We close parentheses, and we want to integrate this from -2 to 2. So if you click on execute, you get the answer, and you see that we get the same result, which is equal to 4. So with this, we once again prove that we can find the area underneath the curve by applying integrals. Okay, now let's see this case, part B. For part B, we have this function, and you see that this is an irregular shape. If we want to find the area of the green region here, we will not be able to do so using a geometric formula, because this is an irregular shape. We do not have any formula for this. We can approximate it maybe to a pentagon, right? But it will not be exact, as we will have some gaps here. So in this particular case, we will not be able to find the area using any geometric formula, but we can find the exact area by applying the concept of integrals, right? Definite integrals. So to find the area, the only thing we need to do is find the integral from in this case, from -1 to 1. So from -1, integral from -1 to 1 of the function. The function in this case is 2 over 1 plus x squared, and with respect to x, right? So if we go to the calculator again, we're gonna find the integral of fraction 2 over 1 plus x squared, we close parentheses, and we integrate this from -1 to 1. Execute, and there you have the exact value. I think this is pi, right? Let's see. If we write pi, yes, it's exactly pi, right? So the area is 3 point, or we can write it as pi. The area is actually pi, which is approximately equal to 3.142, right? So this would be the value of the area of this particular figure. So you see how we can find areas of irregular shapes by applying this concept of indefinite integral. Okay. Let's move on then to, I think we have quite a few exercises yet. So it says exercise 9G. Write down a definite integral that gives the area of the shaded region and evaluate it using your calculator. So basically we're going to be doing the same thing here, just to practice. Whenever possible, find the area using a geometric formula to verify your answer. Okay, so I'm going to go through this a little bit more quickly, because you should already know how to do this. And in the first case, the area is the area of a triangle, right? The area of this triangle, where the base is from -2 to 6. We're moving 8 spaces, I think. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So 1/2 of the base, which is 8, times the height, which is 4. Yes, 4. So the area is equal to, this is 4 times 4, 16. This is how we calculate the area geometrically. And if we use the concept of definite integrals, we're going to say that this is the integral from -2 to 6, right? So the integral from -2 to 6 of this function over here, which is 1/2 x plus 1 with respect to x. If you do this in the calculator, let's see, we're going to find the integral of this function 1 over 2 x plus 1 from -2 to 6. -2 to 6. Find this and you get 16, which is exactly the same result we got. Okay, so this is equal to 16. So once again, we prove that this is correct. Then if we move on to number 2, we want to find this area over here. You see that this is an irregular shape. We do not have any geometrical figure that assimilates this blue region over here. So to find the area, we would just use our GDC and find a definite integral for this expression. Okay, so the area, let's see if I have a space. The area in this case would be the integral from -2 to 0, right? That's our -2 is our lower limit, 0 is our upper limit. Then we write the function x cubed minus 4x, and we integrate this with respect to x. We do this directly in the calculator, and we would get, let's see, the integral of x cubed minus 4x, and we're integrating this from -2 to 0. Execute, and then we get the value. So the value of the area is of 4 units squared. Okay, this is a 4. There, 4 units squared. Then, for number 3, we want to find this blue area here. You see that this is, what shape is this? This is a rectangle. So we know how to calculate the area of a rectangle, right? The area of a rectangle is basically base times height. So the base of this figure is base. Let me write the formula for base times height. So the area would be, the base is 1, 2, 3, 4, and the height is 3, right? From 0 to 3, so 3. So the area of this figure is equal to 12. Okay, so that's how we find it using the geometrical formula. But now, if I want to find it using integrals, let's try doing this by hand, since it's an easy expression. If I do this, the integral from -1 to 3, of this function, the function is only 3, so 3 dx. We find the integral of 3, which is 3x, and then we evaluate this from -1 to 3. I didn't write the plus c anymore because we don't need the plus c when we have a definite integral, okay? So how's the rule? It's we evaluate the function with 3, so this is 3 times 3, and then we subtract minus the function evaluated with this value. So this is minus 3 times -1. If we calculate this, this is 9, and 3 times -1, it's -3, but the negative sign here makes it positive, so plus 3. And you see that we get as a result 12 once again, which matches the result we got here. So the value of the area is also 12. Finally, for this example here, this is a quarter of a circle, right? So we want to find the area by using a formula. We're going to say that the area is pi r squared, which is the area of a circle, divided by 4, right? Because it's a quarter of a circle. The radius in this case is 3, right? So the area is pi times 3 squared over 4. Pi times 3 squared over 4. So this is 9 over 4. So we can write this as, right down here, the area is 9 pi over 4. And if we evaluate this using integrals, let's see if I can do it here. We're going to say that this is, let's see, the integral from 0 to 3. The integral from 0 to 3 of the function, which is square root of 9 minus x squared with respect to x. And if we do this using the calculator, let's see, the integral of the square root of 9 minus x squared, we evaluate this from 0 to 3, and we get as a result this value, 7.0 0.007, right? And let's see if it matches with this. If I put in the calculator 9 pi over 4, this will give me as a result 7.06, which is 7.07, which is exactly the same result. So you see that once again we proved that this works. Okay, so I think I'm going to leave the class here. We're going to see part 2 in another video. I hope this was clear, and if not, please let me know. We're going to clear doubts in future live sessions. Thank you for your attention, and see you.